So, hello everyone. I'm Alex. I'm one of the HPC admins, user support members of the VUB University. And here there's Kenneth. He's also HPC guy, user support from Ghent. And today we are gonna make a small, well, it's not small, but you will find some tips and tricks to how to best approach your work on the HPC, because even if we would like to, working on the HPC can be hard. It's not the same as working on your laptop. Most of you already know that, so you can just not move whatever you're doing on your laptop into the HPC and it will work. That's probably not the case. The HPC is a very powerful platform and it's also very versatile, but this versatility is also what brings a lot of questions and issues that have to be solved in order for you to execute your work in the HPC. So we are gonna walk through some recommendations from our side so that you can better work in the HPC. And the first one, it's kind of the level 0 starting point. Read the documentation. Please, read the documentation. This applies if you are just a student starting, but also if you are already an advanced user, this always applies. In the VSC docs, you will find information about how to set your VSC account, how to manage your data, how to transfer your data, how to use the tier 2 and tier 1 compute clusters, how to use also the tier 1 cloud, the tier 1 data services, and many other tips and tricks, how to write your job scripts, how to find software. There's a lot. You don't have to read all of it, of course. I mean, you just need to check what you need at the moment. But keep in mind, checking the documentation is a good habit in order to avoid issues. And just very recently, we just revamped the design of the VSC Docs website. Now it has a much more modern design, a better navigation, easier search tool. And we invite you just to check it out and also share it with your colleagues so that they know that this exists and it's a modern, useful tool. VSC sites also might provide extra information or extra documentation. The contents of the documentation depends, just be aware of it, and that something useful might be there. And also, at all levels you will find documentation. So the software that you use also has documentation, and that's also very important to check. You would be amazed how many user support requests we get in the support service of our university that we have no idea what they are about. We have zero knowledge about the problem at hand, the software at hand, and that we solve in half an hour just by reading the documentation of the software. It's amazing. So please read the software documentation of the software that you're using. That's always very useful. And apart from that, also there are trainings. So that's probably most useful if you are a student just starting, because what we do systematically at the VSC is provide trainings for students as an intro session to the HPC, and we do those regularly, so if you're a student, check those out. But there are also more advanced trainings that are offered at the VSC level. You will find them all of them in the VSC website. Also, VSC sites might have their own webpage with trainings. Check those out as well. And partner organizations also offer trainings that are usually for free, so those are also interesting. Check them out. Sorry.
All right, so next to the documentation and the trainings, we're also here to help you. So it's very easy to reach out to the HPC support team, ask any questions you may have, any problems you're encountering that you're not sure what's going on, we're happy to help you. It is a bit of a maze in terms of contact points, but it's pretty logical. For tier 2 clusters, there's a support team per site, and basically for each of the tier 1 platforms, compute, cloud, and data, there is a separate contact point as well. If it's a more general question about the VSC in general, you can also email info@vscentrum.be. Before you contact us, please read the documentation first, because maybe your question has already been answered there, and definitely use the search function of the documentation as well, which has improved a lot. Also, don't contact individual people directly, even though it's maybe always Alex or always me who answers your questions. Still stick to the standard contact points, because then we can move around your question inside of the support teams as well.
We take holidays from time to time.
Yeah, sometimes we're not around. It happens, and we sleep too. All right, so you're definitely welcome to contact us, but you may have to exercise a little bit of patience at least. We get a lot of tickets. So the graph on the left shows the number of tickets we've been seeing in Ghent combined for Tier 2 and Tier 1. In 2022, that was 2,600 valid tickets, so no auto-replies or spam or all of that is taken out. So you can do the math, how many tickets we get per working day. It's quite old. So you may have to be a little bit patient. It's not because you're not getting an answer that we're not looking into your ticket. Maybe we're figuring out what happened or trying to trace down the problem in the system, reading software documentation if that's what we need to do to help you. But we will eventually get back to you. Also, to help us help you, it's important that you ask a single question or report a single problem in a single email. So don't ask 5 totally different things in the same email, because that just means you're going to be waiting longer until you get an answer. Maybe you have to, for one thing, ask Alex, for something else, ask Wart, for something again else, ask Balash, and then we need to reach out to all of these people. If you make the separate tickets, we can just send them around and basically parallelize the problem. So that helps a lot. If you're really waiting for something, if you're stuck, and you really need help from us to make any progress, let us know. So make that very clear in the ticket, maybe in the subject of your email, say urgent, or urgent for me, or I'm waiting for this. Maybe send a reminder if you haven't heard back after a couple of days usually. They will try to get back to you as soon as possible, or at least let you know if we're already looking into the problem or not, and if we will be able to help you or not in a short time frame. We also have to look into general issues first. So if the cluster is down or jobs are no longer submitting, for example, and you report that problem, we're probably going to look at that first compared to someone who is stuck with TensorFlow or God knows what. All right, so there is an art to opening good support requests as well. This is a screenshot of an actual ticket we got, I think 2 weeks ago, where someone said the error is shown in the picture. How do I fix this, right? So obviously it's a language we don't know. I'm not even sure if it's Japanese or Chinese. I don't speak enough of that to really recognize it. I see it says Ugand, so that seems relevant, but then I'm stuck. The worst part of this is actually not the language, but the fact that it's a screenshot. So I can't even select the text and drop it into Google to tell me what's going on. But what I can do is I can use my phone and use Google Translate to figure out what the message is. So if we have to, we will do things like this to try and help you, but just don't make us jump through these hoops. You're only making it more difficult for us to help you. So how do you open a good ticket? There's 2 main class of problems here. There's lots of other potential questions as well. If you're having trouble connecting to the system, let us know your VSC account, what operating system you're connecting from. That would be very helpful. Where are you connecting from? Are you in the university? Are you at home? Are you using VPN or not? That all matters. What kind of software are you using? PuTTY on Windows, maybe just SSH on macOS or Linux. What are you using? And also, a lot of the documentation also has like a troubleshooting checklist. So there's sections in the documentation that says, if you're not able to connect, have you checked this and this and this? Like, is there no typo in your VSC account name? It happens, you mix 2 numbers up, and then of course it's not going to work. So all of these things are listed there. And maybe you just want to use the web portal, right? Because then that already solves a lot of these problems straight out. Actually, this previous one, we fixed this by just suggesting the web portal, and this person was happy. So fine, fixed. I still don't know what the error means. If you're having trouble with jobs or software, if you're hitting error messages and you're not sure what's going on, again, mention your VSC account. We're very lazy, so if you have to look it up, it's going to take us time. Mention job IDs, mention the location of your job script in your VSC account, so we can access your VSC account to help you. And we prefer looking at the job script and the output in your account itself. So don't send it as attachment. That again makes it a little bit more difficult for us to actually help you. Let's see what else. Yeah, job output files, keep them where they are. Don't remove stuff. Don't resubmit jobs and overwrite files. That only makes it more difficult for us again. Ideally, also tell us how to reproduce the problem. So after login, which steps did you take to hit that problem? Which job script did you submit? How did you submit it? All of this may be relevant. Now, usually if you say, I have a problem, my job doesn't work, and you just send the email, the first thing we're going to ask you is to provide all of this anyway. So you might as well do that straight away, and that's going to shorten the time for us to help you. And if you can avoid it, don't send screenshots. If it's a GUI application, of course, that's difficult to prevent, but if you can, copy-paste the error messages so we can drop them into Google and do some searching. That brings me to the next slide. If you are searching yourself, which you should always try yourself, using standard search engines like Google or DuckDuckGo, first of all, read the error message. Maybe the clue is in the error message itself. I do admit not all error messages are good or are easy to understand what's going on, but that's definitely the first thing you should say. Just don't say, oh, there's an error, I'll send an email. Try to understand what's going on first, maybe you can fix it yourself. If you are Googling, use a good search query. Use it in English, so don't use Dutch words, French words. It's usually better or easier to find good answers if you're using English. Try to only use a handful of important words. So kick out anything that's not relevant, like the or or error. It's unlikely to be helpful. One very key thing that many people don't seem to know, if you have an error message, like here, out of memory, put quotes around the out of memory. So Google or DuckDuckGo treats it as a whole thing. It doesn't look for out and off and memory separately, and then God knows what it will find. So that can be very useful. You can also filter out irrelevant hits by using negative terms with a dash. So the example there is we're looking for help for Python pandas, and we don't really care about animals. We do dash animals to kick out these results. You would be surprised how much better the results are if you start doing things like this. When you do hit an answer that looks relevant, especially on sites like Stack Overflow, take into account the date when the answer was posted. If you're looking for help with TensorFlow and you find an answer that was posted 5 years ago, it's probably not very relevant anymore. TensorFlow has changed a lot since then. So you may want to be careful with applying that answer. Also, in what kind of context was it answered? Is it someone who figured out how to fix the problem with a sudo command, so running a command with administrator rights? That's not going to help you because you don't have administrator rights on the system either. You can try, it's not going to work. And also, like Geert-Jan was already hinting to, you can definitely try ChatGPT. And it can be a lot more useful than a search engine, but just be careful what it tells you, because it may be flat out lying to you, like hallucinating, or again, the context in which you ask the question may be very important as well.
Okay. So, next step is always, as a general advice, always try to plan your strategy in the HPC. So that means if you're going to start working on some project on the HPC and some of your colleagues is handing you over some job scripts or some just input files, or you're just copy-pasting stuff from your laptop to the HPC, that's probably not going to work. So even if it's already run by some of your colleagues, if they did not run it exactly in the cluster that you're going to use, it's probably not going to work. And also different HPC clusters have different hardware resources, which means that you can do different stuff, different amount of stuff, different quantity of jobs. And it's also important for you to plan that stuff beforehand so that you know how much you will be able to do in a time span. And this will also limit the scale of the problem that you will be able to solve. Planning ahead is good because you will be faced with many questions that you are going to hit anyhow during the execution of your project. And there are many. Here, this is just a list of like how many CPU cores I'm going to use, how much memory will I need, do I benefit of using GPUs or not? Is that beneficial for my work? How much data I'm going to use? Do I need data as input? How many data is going to be generated by my program? How am I going to store the data? Where? How I'm going to transfer the data to somewhere else to be analyzed, to be post-processed? All those questions, it's important that you answer them as soon as possible, because if you hit any of the limitations of the HPC, which there are limitations, you don't want to hit those just the week before of the deadline of your project. So you're going to know those in advance and prepare beforehand. So what I'm going to show you now is a few examples of common workflows, strategies that are in use in the HPC right now, that what we see that users do and may apply to you, and what are the main pitfalls, questions that you will hit if you are carrying out one of those in your project. So the classic case is the MPI application. MPI applications are applications that use the network to distribute a workload across multiple nodes. That means that the execution of the simulation is going to be automatically partitioned in some amount of CPUs, and those CPUs can be located in different nodes, and the application will use the network communication between the nodes to actually handle the execution of that program. In that case, that allows you to scale up to your problem very easily, because just by adding new nodes, usually you will get more power, and that means you can carry out larger problems. But also means that the network speed between the nodes becomes a factor that you have to take into account to determine the performance of your simulations, and that might be limiting. Don't carry out MPI simulations on nodes with slow network connections, because that's not going to perform well. And also in this case, you can really think big. So for instance, if your application falls into this category, start thinking about using Tier 1, because Tier 1 is really designed for these kind of applications with fast network and a lot of nodes that you can use. Also, in terms of software, keep in mind that MPI needs a special treatment, let's say, to be installed properly in the cluster. So if your software needs MPI and it's not already installed and available, ask that in advance with some time, because those installations might take more time to carry out. And finally, the storage. Since the nodes, you will be executing your applications in multiple nodes, you will need access to a shared storage. All the HPC clusters in the VSC have a shared storage, but pay attention to use a fast one. Usually that's the Scratch, the VSC_Scratch. And also keep in mind that if your MPI application is very I/O intensive, you might be limited by that. So your bottleneck will not be the amount of nodes, the amount of CPU power, but might actually be the storage that is limiting your simulation. So those are the questions that you might face in this case. Another case is kind of the opposite. That's what we call the task farming or job arrays. Those are those applications where there's not a lot of parallelization. So you carry out tasks with some software that works on a few nodes, on a few CPU cores, I mean, so 2, 3, 4 cores, but you have many of them. Like imagine if you have a big data set, a big data collection, and you need to execute the same task on a lot of data points. And those tasks are actually independent, so you don't need to start from first to last, so you can just distribute that in parallel over the cluster. In that case, the communication between the nodes is not relevant, because you will be executing independent tasks in each of the CPU cores. So that's one variable that it's taken out. However, you have to keep in mind how to organize your jobs, because in that case you will have thousands, well, hundreds or thousands of tasks, and then you need to actually plan how are you going to execute them. There are different solutions for that, and you will have to set up something that can do that automatically for you, because you don't want to submit 100 or 1,000 jobs manually to the cluster. And for that you can use job arrays, which will create one job per each one of the tasks. But that might not be optimal, because if your tasks is very small, like it can be completed in a few minutes, then you will create one job of 1 minute in length, and that's a lot of overhead for the cluster. So this is also not optimal. Then you might want to group those tasks. And for that, there are tools like new parallel or workers that can help you in actually distribute groups of tasks in the cluster. So keep that in mind as options. Also, in those cases, it's very common that each task are going to generate one output file, for instance. And then you might end up with a folder with 1 million output files. That's also not good at all, because there are limitations on the number of files that the storage system can handle. Also, just by the fact of having 1 million files in a folder, any access to that folder will be slow. Even if it's just to check and list the contents of the folder, that's going to be slow. So you want to avoid that. And for that, you can just simply use subfolders to organize those files. That's kind of the simplest solution. But there are also more advanced solutions, like using hierarchical data formats like HDF5, which serves a kind of a small database in a file where you can just store chunks of data with metadata inside a single file, and that does not strain the file system at all. Also keep in mind that if you need to do post-processing, each of the individual tasks might not be executed at the same time. They will be just allocated as the sources are available, which is very flexible and allows you to take benefit of the what we call the holes in the cluster that are available. But also keep in mind that to do the post-processing, you will have to wait for the last task to complete, so that might take a while. Then we have the IO-intensive jobs, so those jobs that actually hammer the hard drives of the cluster, and those commonly are the bioinformatic pipelines, because those usually work a lot with genomic databases, for instance. And then there's a lot of reads and writes, and also that the problem of those applications is that the readings actions are quite random, so you just don't read from the start of the database to the end. The program will just start randomly jumping along the structure of the database. And that's straining for the file system, and not all storage systems are equally prepared for that. So be aware, in that case, of the different storage solutions available in your HPC cluster, because those will matter for your application. And in terms of software, the question that you will be faced is that these pipelines might include many different software packages. Like, I'm talking about 100 different software packages. To get those installed in the cluster is not trivial, and might take some time if they are not already installed. So also plan ahead if you need software to be installed for these pipelines, because the quantity of software is not negligible. And finally, at least that might change from cluster to cluster, but those genomic databases might be also already available in the cluster. So in that case, you don't need to account for any storage quota in your account to store them. And next we have the GPU jobs, which are now very much in demand due to the new machine learning workflows, but which are also used by molecular dynamics. And in that case, the questions that you will be faced is, well, first of all, GPUs are more limited resource than CPUs. So keep in mind that if you are going to rely very strongly on GPUs, the queue for GPUs might take some time of the time available in the cluster. So keep that in mind. Also, check the GPU memory of the GPUs, because that also matters for your applications. And that's not something that is really managed by the HPC cluster. So there might be GPUs in the cluster with different memory. Check that memory available, the video memory in the card, because that will determines usually the size of the problem that you can carry out in the GPUs. Also, CPU power for the GPUs is important. Your job will carry out some preparation of the data for the GPU. And that takes time, that takes processing power, and that might become the bottleneck of your job if you do not request enough CPU resources for your GPU job. So take that in mind. Finally, in terms of software, software cannot use the GPUs just out of the blue. It needs a specific support for GPUs. That's either by using the CUDA libraries from NVIDIA or the ROCm libraries from AMD, depending on the GPU that you're using. Keep that in mind. Even if the software that you're going to use is already installed, check that it has support for these libraries, for CUDA or ROCm. Otherwise, it won't work in the GPUs. And if it doesn't, request the installation. And finally, also keep in mind that there are many tools to actually monitor the execution of jobs on GPUs, and that you can use those in the HPC as well, like weights and balances and the Neptune client or TensorBoard. So those are all options that you have. And finally, for those of you that are interested in using notebooks and a graphical interface, also keep in mind that the workflow there, it's different than if you just submit classical job scripts. And the interactive interfaces like the notebook platform might give you some resources that are shared with other users. That's what is usually called oversubscription. For instance, that's the case in Gantt. You can just, as Ewald showed, a debug node. That debug node has shared resources, so that's not meant to actually carry out production runs, that's just meant to test. And that might be the case if you don't pay attention to what resources you are requesting, so pay attention to that. Also, time limits might be shorter because usually these solutions are meant for a person to actually work actively on the problem. So probably it's just limited to 1 working day, that's the approach. If you need to submit some simulation that runs for days, you have to think about submitting a job script. Even if you do that from the interactive platform, that should run through a job script that will be allocated in the HPC cluster. And finally, yeah, you can also try to start interactive sessions on dedicated resources that are only for you if you really need to do compute-intensive stuff. So those are the options that you have with interactive workforce.
All right, and then let's take a look at how you can really speed up your work hands-on by looking at some tips and tricks in the Linux shell environment. So like Ewald already showed, there is a web portal for most of the VSC resources, which is very helpful, but that doesn't mean you can fully get away from the Linux shell environment, or that you should, because it's actually a very powerful environment. It feels very archaic. I think Ewald called it 80s, which is not a lie. It's been around since the 80s, even longer than that. But that doesn't mean it's not very powerful. So everything I'm going to be showing here is you can use these interactively hands-on while submitting jobs or navigating the system. And most of the things you can also actually use in JavaScript. So it's the same language as you use in JavaScript, which is very important. I have a couple of slides for this, but I actually prefer showing it as a demo. So Alex will have to hold the mic because typing with one hand is very difficult.
Yes.
All right. So what I'll do is I'll use the web portal for this, but I'll basically, I need the firewall app because I disconnected my VPN. So what I'm doing here is just trying to get shell access directly in the browser. So I'm not using any tools like PuTTY or even just SSH on macOS. This will take a while. We'll have to refresh, but it shouldn't take too long. Of course, demos always go wrong. All right, there we go. So we're getting shell access, in this case, to Hortense. And let's see if I have set things up correctly. I look like it wiped my basher C, so I'm well prepared. I have a subdirectory here with some files in it that I prepared for the demo. Now, one of the first things that you already see me navigating around with commands like cd, ls. That's pretty basic. That's like the first thing you should learn when using the shell environment. And one thing that's very important is there's documentation in the system itself. So there's man pages. So for example, for the cp command, you can run man cp, you hit enter, and you get documentation of the cp command with all the options that it supports. You can search through this if you hit slash and you look for a name, let's say permissions. Of course, that doesn't work, or directory, whatever. You can start looking for options that relate to directories. Like cp-r allows you to copy directories recursively with everything in it. If you want to exit the man page, it tells you actually at the bottom, you hit Q for quit. Right, so there's built-in documentation in the system itself, which is very, very nice to know. Now, one thing, especially if you use the shell a lot, is you'll find yourself repeating the same commands over and over. And the shell has actually remembered what you've executed before. So if you use the up arrow, you can cycle back and see which commands were being run before. That's very useful. Now, don't play the game of keeping hitting up until you hit the command you found. There's a more powerful way. You can do Control-R. This puts you into search mode. And here you can look, for example, the last echo command I ran, or the echo command before that. So you hit Control-R again. You can find what was there in your history. You hit enter, and it's running the command. So if you're a very lazy person, like most computer scientists are, you can save yourself quite a bit of keystrokes. This is mostly relevant, of course, if you're running really long commands or very complex commands. What else do we have here? Oh yes, tab completion. So this surprises a lot of people as well. So here we have a file with a very long name, and I can try typing this. Let's say to see the contents, I can do file with very long, and it's not going to take me long before I make a typo, right? And then I hit enter. Oh, it doesn't exist. I have to start over again, right? Very annoying. There's actually tab completion, so you can start with the name of the file. In this directory, there's only one file that starts with file, so I can hit the tab button on my keyboard and it auto-completes the whole thing. Right, so if you don't know where the tab key is, it's above the caps lock on your keyboard. People who know the Simpsons, like the tab key, the bird hitting the tab key, that's what this is for, tab completion. All right. So yeah, you can type like a ninja by using type completion. If people don't know type completion and they see you typing, they're going to type, wow, this guy is fast. You're not, you're just cheating, basically. All right, what else? All of these small commands that are available in your shell environment, you can combine them and do really cool things. So ls is very basic. With head, you can look for the first number of lines in the output. With grep, you can do basic pattern matching. And you can combine all of these things by building command pipes by using this pipe command. So let's see how that works. We do ls here. I'm only interested in the input files, so I do pipe, I grep for input for a particular pattern. Oh, that only gives me the files with input, good. What was the example again? I need the first 5 of those, so I do head -5. That gives me the first 5 lines. Then I want to make sure, actually the example is not fully correct. I'll grep for text. Let's say input.text instead. The first 5 text files. I want to find if there's a corresponding dat file for that, so I'll do replace.txt with .dat. So that's what the set command can be used. And then here I can pass this to another command to show which files are hitting that. I'm getting errors here. I want to get rid of the error, so I can get rid of the error output by piping it to dev, or sending that to dev null. So now I see for the txt files that I had, the first 5, which ones have a corresponding dat file, and I can see the timestamps of that. So you can very quickly build a rather complex task by combining all these small commands together. And you can just build it up like I did, step by step, and think which commands can be useful for the task you have in mind. People who are used to working in the shell environment do this all the time. So that's a very important skill to learn. Also here, impress your colleagues by doing this. Another small trick, but a very useful one. If there's some commands you're executing all the time, you can define aliases for them. So what's the single fastest command to type? It's one with a single letter, right? And you can define your own. So I think my history got messed up, so I'll have to do this from scratch. But I can say, if I want to print echo hello VSC, I can define an alias for that, and then if I hit X, enter, it will do that command for me. Now, in the case of an echo, it's pretty stupid, but imagine you're running on the Milan partition of Hortense all the time, right? Then you're probably used to typing a command like this, module swap cluster doodle CPU, oh boy, that takes too long. You define an M alias for that, you hit M, and it switches to the CPU partition of doodle. So that's very useful. You can do more complex stuff as well with functions and so on. And there's actually already a built-in alias that many people don't know about. So if you want to check which modules are loaded, you can do a module list. But it's very easy to mistype module as well, right? And then you get very confused and annoyed again. There's a shorthand called ML. So ML is short for module list, or it's short for module load if you give it the name of a module to load. So now it's loading that module, which takes a while, and then you can run module list or ML again to see what was loaded. You can use ML also with swap or avail or any other commands that if you're not mistyping, of course, like avail, you don't need to type avail, just AV is enough. So the system is full with these shorthands and faster ways of working. So try to get used to them and try to use them. All right, that covers most of this. So you saw me defining aliases. If I log out of the system and log back in, those aliases are gone because they're not saved anywhere. But you can save them in your own startup script. So here in my startup script, I'm defining additional environment variables, like this VSC scratch project space thing. I get so sick and tired of typing this. So I have a shorthand SPB. So I can just use $SPB wherever I use this environment variable. The M alias I've defined before, if you store this in a file called .bashrc, which is a standard shell startup script, you can run them. Yeah. Right, I won't demo this, but you get the idea of how this works. All right, and then back to Alex.
So, as I said before, one important thing that you will have to handle is storage. Not all folders in the cluster are equal. There are different, even in a single HPC, you will find different storage systems, and each storage system will have different characteristics of performance, reliability, availability. So it's good that you know them, because that will determine where you put your files and what's better to put your files on. Basically, in the VSC clusters, there are 4 main different solutions that you will find everywhere, and that's where your home directory is, and that's usually a very small partition that it's not meant to hold any important files or data about your research projects. That's just a small directory for configuration files, small things, should not be used in general. Then you have your VSC data storage, and that's what you'll find inside the VSC data folder. So these $signs that I'm showing here, that means that this is a variable, and you can work with this variable as any other folder name. So you can do the cd command, the change directory command, to VSC data, and then you will move to that directory. And the same for all the others. And usually VSC data is larger than VSC home, but it's not the larger partition. But VSC data is a partition designed to actually hold important data. So all that data that is basically a result of your jobs, but that you want to keep because you need it for publications, for archival, for whatever. And the VSC data storage is also available across all the VSC sites, all the clusters in the different VSC sites, so you can access your same storage in VSC data in Ghent, in Leuven, in Brussels, everywhere. And performance is relatively low. It does not mean that it's slow storage, but compared to the Scratch that I'm going to talk about later, it's low, so do not expect full performance out of it. However, it's very reliable. Usually these storages work on what it's known in the IT world as RAID storage, which are very reliable. If a hard drive, if some hard drives fail in the storage, that's not an issue. Your data is safe. There are also backups of the data in VSC data, so that's also an extra layer of safety for you. But as I said, it's not the more performant one. So if your job really needs performance and it's sensitive to the IOs, to the storage, because you are going to read and write a lot of files, or there's a lot of data to move around, then use the Scratch. And those are larger. You get a larger quota in the Scratch. It's only available in this cluster that you're going to use, because it's a shared storage, but it's shared across the nodes on the cluster, but not across the different clusters, as VSC data is. So keep in mind that whatever data you put in the VSC Scratch is only going to be available in the cluster that you're using at the time. Also, it's very reliable because it's also a RAID solution, so if hard drives fail in the Scratch, your data is safe. However, usually there are no backups, so do not expect, if a file is deleted, even by you by accident, you won't be able to recover it. And some sites might have policies of cleaning up data in the Scratch from time to time, like once a month, or when you don't use some folders for a long time. And finally, there's the temp directory, or the local Scratch in the nodes. That's a very variable storage that you get for whenever a job starts. It's specific to the job, it's not shared between nodes, it's not shared with anybody else, not across clusters. It's just for the job, allocated to the specific job. And it's a local storage that is local to the CPU cores that you are using in your job. So it's, in general, very fast, and it might be necessary to use this storage for applications that have high I/O patterns, like the bioinformatics pipelines that I was talking before, that have a lot of random reads and writes on databases. Then using the local storage on the nodes, which usually are SSD drives, might be the preferable solution. By default, though, if you are in doubt on what to use the VSC Scratch. It's usually the solution that will constrain you less. You will have the largest quota, better performance. It's a shared storage across the multiple nodes, so you can run MPI or whatever solution you need. So you can start with VSC Scratch and move to other solutions if your application needs it. And Also keep in mind that the storage is the slowest part of the cluster, probably. So it's what, if your application is sensitive and there's a lot of writes and reads to the file system, that's going to become the limiting factor of your job, probably. And also the capacity, so there's a limitation on the amount of I/O that you can get out of the storage, but also in the capacity, and actually the storage is shared across the users. So if there are a lot of users hammering the storage, you will see that your job might run slower because of that. So it's a good practice to actually, try to use as much as possible the fast storage. So the scratch, or even a disk memory in RAM. And for instance, you can set up that in your jobs with very few lines of code. So for instance, usually you can always access the /dev/sgem storage from a job. That's storage that you can access as a file system, like with folders and files, but that actually lives in RAM memory. And that's very, very fast. Or also you can set up, with a few lines of code, an automatic way of moving data between VSC data and VSC scratch, so that your important data lives in VSC data, because that's the reliable storage, but then you want the fast performance for every job. So you can just, in a few lines, just copy data to the scratch, run the calculation from there, save the data that is needed to the VSC data, and that happens all automatically. And finally, as I said before as well, number of files matters. There's a limit on that. Keep an eye on that. Organize your data in a way that you don't end up with 1 million of files in a folder. And to transfer data in and out of the cluster, try to use Globus as much as possible. That's the best performance solution by far, because we have set up a specific workers and agents of Globus in the cluster that can move your data very fast, because they can work in parallel, so we have multiple agents running. Also, it offers you a lot of flexibility, so you, for instance, can schedule transfers of data that happen every X time, like every week you need to transfer data to some other server out of the cluster. You can do that and set that automatically. Also, you can share data with your colleagues easily by just sharing a link or setting up a shared folder. So that's definitely the best solution if you want to move data.
Right, we're almost done, and we'll go a bit quicker so we don't stand in between you and the reception. You can also manage your own software stack. So this has been hinted at a couple of times already. We provide a lot of software on the systems out of the box. But if you want and can manage the software stack that you need yourself, you definitely can. There are some caveats here. Ideally, the software that you're running should be compiled for the specific systems, for the specific CPUs, for the specific network or GPUs that you're using in your jobs. If you ignore that fact, the software may still run, but it's probably going to be a lot slower than it could be. So that's an important detail. Very often, if you try managing your own software stack, you will end up like this person there on the right. So that's why you can also ask us to help you. So you can do software installation requests, especially for standard releases of software that needs to be compiled from source, like C++ or Fortran. Software that's very performance sensitive, that relies on libraries like MPI or CUDA, like Alex already mentioned. Or if you're just stuck and you're ready to give up, send us an email and we can probably help you. We literally have experience with installing thousands of different software packages, so the problems that you're hitting, we've probably seen already and we know how to fix them. If you do an installation request, again, you'll have to be a bit patient. We get a lot of these. I think in Ghent, for Tier 2 and Tier 1 combined, we get about 350, 400 requests per year. So that's multiple per working day. And some of these are not a pip install, but something way more complex. So it does take time sometimes. We work together on EasyBuild to make it a lot less painful. If you're ready to try it yourself, you definitely can. This is mostly recommended for if the software is implemented in a language like Python. So if it's a pure Python package, only Python code, then it's usually a lot easier. Same goes for Perl, Java, all of these interpreted languages. You can also run EasyBuild yourself. So you don't need any special rights to run EasyBuild. You can run EasyBuild in your own account on top of the software that's already installed, and just add the missing parts, essentially, install your own modules in your account. If you're developing the software yourself, if you're a C++ programmer, this is probably a lot less scary for you than it is. But even then, if you need help, again, don't hesitate to reach out to us. A couple of tips, if you're compiling, especially compiling software yourself, try to do it on the cluster or the partition of the cluster where you will also be running that software. That can be important in terms of getting good performance. If you're using DCC as a compiler, -mRGnative is a very good option. It basically tells the compiler optimize for the CPUs on which you are running as a compiler. So you're going to get optimized installations of your software like this. Intel compilers have similar options. If you're compiling with Intel compilers on AMD CPUs, it gets a bit more tricky because these two don't really agree for some reason. They're competitors, of course. There's some special environment variables that are predefined if you want to build binaries specific for a particular type of CPU or a particular operating system, you can use these environment variables. And for very complex software packages, PyTorch and OpenFOAM, TensorFlow are good examples of that. We don't recommend to install these yourself or to try and compile them yourself, because you'll very quickly end up like the guy in the corner. Like Ewald already mentioned, if you're using container images, especially pre-built container images that you found somewhere on the web, or if you're using Conda or Mamba to install the software yourself, be careful that there may be trade-offs there. So the software that you're getting may work, but it may run a lot slower than it could if it's properly compiled from source and optimized for the CPUs. Now, getting it to run is the first step, of course, so you can definitely still try this. This is a small example of setting up a Python virtual environment. So we're loading a module for PyTorch. We're running Python-venv and -mvenv to set up a virtual environment. And we're doing a pip install of this Poutine package, which needs PyTorch to run. So rather than installing PyTorch with pip, we're using the PyTorch that's pre-installed on the system, and we're installing extra Python packages on top of that. You can definitely do that yourself. And then also use it in a job script, of course. Right. Okay. I think we have half a minute for the rest.
Okay, so I'll go fast. So now, when you start writing a job script, as I said, you'll have to answer many questions. Basically, how many cores I'm going to use, how much memory, GPUs. Just keep in mind, just adding more might not help you. It will probably not help you. You have to first check that your software can benefit from all these extra resources. So the strategy is usually always the same. Start small, prepare a job that can use only one core, and use that to actually verify that the code in your job script works, that your input scripts also work, check the parameters of your application, and tune that to a point that it runs. Then after, you can start with the parallelization test. That means increasing the number of CPU cores used by your application and see if that helps. I mean, check the documentation first. If that's something that is useful for your application, does it support MPI? Does it support running in parallel in multiple CPU cores? Check that. If that's the case, increase the number of cores, adjust the options of your application so that it uses those cores, and then check how long does it take to complete. Is it better? Is it not better? If it's significantly better, you can then repeat this step, increase it even more, and check what's the evolution of the time to completion. At some point, different things might happen. So it will improve usually. If it's an application that supports parallelization, it will improve to a point where probably it hits an out-of-memory error. Because maybe by using more cores, the applications usually need more memory. Your job will get more memory proportional to the number of cores, but if this relationship is not linear, you might hit an out-of-memory error. In that case, the solution is also to just double the memory. Ask for more memory, you can do that. Check the limits of memory in the nodes that you're using, because there's of course a limit. But you should be able to double the memory and then check if it works. If the job now runs, and check the time that it took to complete. If it's not better, go back and reduce the scale of the parallelization, so go back to a lower number of cores. If it works and it works well, just go ahead and continue further. And then at some point you will either get a wall time error on your job, and if that's the case, the solution is just to increase the wall time. Different clusters have different time limits, so usually for tier 2 is 5 days, for tier 1 is 3 days. Keep that in mind. Increasing parallelization might help you reduce the time that your job takes to complete, but also it might not be a linear scaling. So at some point you will hit a limit. So keep that in mind. And once you find the optimal combination of resources, then you know that you have the setup for your production runs, and you can just submit that at scale. Finally, to monitor how much memory was used, how many compute CPU power was used, there are different tools. At all time, when a job is running, you can actually open an interactive session into the environment of the job with that srun command that should work in all clusters in the VSC. And then you will get an interactive shell in the environment of the job, and then you can just use any Linux command to actually check resources like top, htop, and all these variants. Also in Nick's demo, we have a web platform where the resources used by jobs are locked into that. And there are different commands that you can use in the Linux terminal of the system to actually monitor how much resources were used by jobs that have already finished. So all these 3 different options is for jobs that have already completed.
All right, this is the last slide. The main message here, tricks to get your job started faster, is factor in the queue time of the jobs. So the more resources you ask, the longer your job may be waiting in the queue, which means you are waiting for the job to finish as well. So there's tricks to limit that. You should look into the different clusters that are available. Maybe try submitting to another cluster. Look at the clusters of the other VSC sites. With your VSC account, you can actually get access to all the VSC resources, at least tier 2. Maybe you want to consider submitting a tier 1 proposal if you're doing really big stuff. That's definitely makes sense. There's more resources. There's also fewer users there, so the queues are typically shorter. And there's, as Alex already mentioned, very often also an interactive and debug partition where your job starts straight away, but with a very limited amount of resources. One thing you can also consider to limit the amount of time in the queue is asking for fewer resources. Your job may become slower, but maybe it starts instantly. So in terms of waiting time, you're actually waiting a lot shorter. Something that I found helpful for small jobs is to ask for a quarter node. So if there's 100 cores in a node, ask for 25, and usually your job will start very, very quickly. So that's a nice trick. And of course, this is a balancing act as well, in terms of what you need. All right, so to wrap things up, how to get your work done faster, take a look at all the tips and tricks, read the documentation, and that's probably going to help you quite a bit to get your work done faster.